Welcome to BBS Pragati channel. In this session, let's have a look at some more important design considerations of broadband MMIC switch using gallium arsenide MESFET. So the important design consideration is the dissipative laws associated with MESFET switches and microstrip lines. Now here the MESFET is used as a switch, so it's a passive device. Hence you don't need heat sinking. And further, if you want to, sink the heat, you can use a relatively thick substrate. For the switching FETs, however, RF losses are much greater and are associated with the parasitic resistance of the device. So, considering this, the important design consideration, that is the quality factor, has to be defined. And it is quantified by figure of merit Q square, where Q square is equal to R off by R on. And R on, so you know that a MESFET as a switch is a resistor in its on state, and its off state, it is a capacitor in parallel with R off. So Z off is equal to 1 by R plus j omega C, which is equal to R minus j omega C R square by 1 plus omega C R whole square. So you know the various values. So ultimately Q square will be equal to R on into R inverse WC to the power of minus 2. So we see that even if the gate width is increased, Q square increases with frequency. Okay. So what is very important is you should choose a gate width such that you get a reasonable insertion loss and a isolation. Now let's understand about one more important design consideration, that is a switching speed. So the switching speed can be analyzed by using a simplified switch MESFET which is connected to a control source with output resistance R0. Okay, and there are certain assumptions. We consider that the main contribution to the switching time comes from the gate resistor RG, which is of higher value, and the junction capacitance CJ. And we also consider the inductance between the control source and the MESFET is negligible, hence that can be neglected. RF load is far less than RG, hence that can be neglected. And so once we have considered all the assumptions, so the switching circuit is a RC network, and it has a RC network behavior with the time constant twice R0 plus RG into CJ. So the delay time in the off to on transition is equivalent to the time it takes for VG to change from its initial value V off to a value close to VP. So that during that time, the R bias is 5 kilo ohms, C off is 240. So you get 2.4 nanoseconds. Okay. So here is an equivalent circuit